Hello everyone, I am Amit Maru, and today in this video we will discuss about traversing a graph by using depth first search algorithm. This is the topic of exploring graph of analysis and design of algorithm subject. So let us start our today's video on traversing a graph through the depth first search algorithm. To traverse the graph or to visit different node of the graph, we have a certain method. Using that method, we can visit a different node of the graph. The first method, that is a breadth first search method. We already discussed this method in our previous video. In that, we are using queue data structure to visit different node of the graph by using breadth first search algorithm. Then next method, that is a depth first search algorithm. In that, we are using stack data structure. So today in this video we will discuss about depth first search algorithm. Again I am repeating, we are using stack data structure to visit different node of the graph in our depth first search algorithm. In depth first search, the algorithm starts at a root node and explores as far as possible along each branch before backtracking. So before understanding the example of depth first search algorithm, let us have some steps how we can visit different node of the graph by using depth first search algorithm. So let us discuss different steps of depth first search algorithm. Step number 1, select any node as a starting node and mark it as visited and then store it in stack. As we already discussed, we are using stack data structure in our depth first search algorithm. So initially at a starting level, we have to consider any node as a source node or a root node, and then we have to visit this node and we have to store this node inside our stack. Then the second step is identify neighbor node of it and select any one node. Now the second step is we have to identify all the neighbor node. It means that we have to explore that node and we have to identify all the neighbor node, and among this all the neighbor node we have to select only one node. Step number 3, marks that selected node as a visited node and store it in stack. That selected node we have to visit and we have to store inside the stack. Step number 4, repeat step 2 and step 3 until we get neighbor node. Once we can't explore the node, it means there is no neighbor node, at that time we have to stop. Then we have to follow step number 5. Once there is no any neighbor node of selected node, then perform pop operation and repeat step number 3 and 4 again. So now we have to perform pop operation once we cannot explore the node. When we perform pop operation with the stack, at that time last inserted node will be removed from this stack, and then again we have to perform same operation, that is we have to follow step number 3 and step number 4. Last step stop when there is no element in the stack, or we can say when we visit all the node of the graph, then we have to stop. Let us understand same steps with one example. Suppose we have one graph and this graph has different nodes and different edges. As we know that in our depth first search we are using a data structure, that is stack, and stack follows a last in first out pattern. So this is our stack, in that we will store different node of the graph, and this is the output where we will print a different node as per the depth first search algorithm. So let us follow all the steps to solve this problem to visit different node of the graph by using depth first search algorithm. As per the step number 1, we can select any node as a source node or root node. Either you can select S as a starting node or source node. You can select A, B, C, D, any node from the graph. So for example, if we select S as a starting node, then the first step is we have to select any node as a starting node and we have to visit it. So we have to visit S and then we have to store inside the stack. When we store inside the stack, at that time stack has a one pointer, that is a top pointer. This top pointer basically used to point top of the stack. So when we store S, at that time top will point to the first element, that is S. Now we have to visit this S, so that we have to print as a output. So S will be printed, or we have to visit the S. So first we have visited our node, that is our S. Now step number 2, we have to explore S, and we have to identify all the neighbor node of S. S has a 3 neighbor node, A, B and C. So among these 3 we can select any node and we can visit any node. Either we can select A, B or C. For example, if we select A, then we have to visit this node first, and then we have to store inside the stack. When we store inside the stack, at that time top will be increased by 1 and our element will be stored here. So this is the first element and this is the last element inserted inside the stack, and our pointer will point to the top of the stack. So A visited, so that we have to print it as a output. So we have to print A. Now our top is pointing to the top of the stack, that is our A, so that we have to explore A now. It means that we have to identify all the neighbor node of A. So A has a 2 neighbor node, one is S and second one is D. So now we cannot select S because S already visited, so we have only one option, that is D. So now next we have to select D. Now visit D and then store inside the stack. So again top will be increased by 1 and will be stored a D inside the stack. So D is already visited, so that we have to print D as a output. Now our top of the stack is the node number D, so that we have to explore D and we have to identify all the neighbor node of D. D has a 3 neighbor node, one is A, B and C. Among that A is already visited, so we have a 2 possibility, either we can visit B first or C first. So among these both the node we can select any node. Suppose we select B, then we have to visit B first and we have to store B inside the stack. So increase top by 1 and store B inside the stack. B is already visited, so that we have to print B as output. So B printed. Now next step is our top of the stack is B, and so that we have to explore B, we have to identify all the neighbor node of B. Now B has a 2 neighbor node, one is S and second one is D, but both already visited, so we cannot visit S or D. It means that no any neighbor node of B which is unvisited. So we have to perform pop operation. So let us perform pop operation with the stack. When we perform pop operation, then last in first out, it means that last element of the stack will be removed. So the last element of the stack is B, so B will be removed from the stack. Our top will be decreased by 1 and B will be removed from the stack. Now our top of the stack is D, so we have to explore D again. We have to identify whether any node of B is still available which is not visited. So D has a 3 neighbor node, one is A, second one is B and third one is C. Here A and B both already visited, so we have only one option, that is C. So now we can select C first. So select C, visit this C and then store C inside the stack. To store the C node inside the stack, we have to increase top pointer by 1 and then we can store C inside the stack. Now C already visited, so that we have to print it as an output. So C printed. Now next step, that is we have to check top of the stack. The top of the stack is our C node. So we have to explore C, we have to identify all the neighbor node of C. So C has a 2 neighbor node, one is S and second one is D. So as S already visited, D already visited, so that we have to perform pop operation, because there is no any neighbor node of C which is unvisited, so that we have to perform pop operation. When you perform pop operation, at that time top will be decreased by 1 and C will be removed. Now our top of the stack is our D node. So we have to explore a D, we have to identify the neighbor node of D. D has a 3 neighbor node, A, B and C. These all already visited, so that we have to perform pop operation again. So reduce top pointer by 1 and remove D from the stack. Now our top of the stack is A and we have to explore A. A has a 2 neighbor node, one is S and second one is D, both already visited, so that now again we have to perform pop operation. We have to reduce top by 1 and we have to remove A from the stack. Now the last node, that is S, is available inside the stack, and we have to explore S. So S has a 3 neighbor node A, B and C. This is all the node already visited, so that we have to again perform pop operation from the stack. So S will be removed. Now our stack is empty. So we have visited all the node of the graph, and the sequence is, first we have to visit S, then after A, then D, B and C. It means that we have started from S. S is our starting node. Then we have to visit A, then after D, then after B, then after C, as per the depth first search algorithm. If we remove these remaining edges like S to C and S to B, at that time we have one tree. This tree is known as depth first search tree. So this is our DFS tree. Now let us understand the pseudo code of our depth first search, or we can say the algorithm of depth first search. This is the recursive algorithm for the depth first search. As per the recursive algorithm of depth first search, we have to call one function DFS and we have to pass V as a argument. So V is nothing but our starting node. We can consider any node as a starting node, and we have to visit directly this node. Then we have to check each vertex of X adjacent of V. We have to identify all the neighbor node of V. Among that we have to select one node which is not visited, so that we have to check if visit of X equals 0. It means that the node which is not visited. If yes, then we have to visit this node. It means that we have to pass this node as an argument, and we have to call same function again. This function call itself is known as recursion. Right? So this is all about our depth first search algorithm. Every time we have to select a node, all the neighbor node, and we have to select only one among that, and we have to use stack data structure to find the sequence by using depth first search algorithm. So thank you very much for watching this video. Thank you.